So now what I need to do is that I need to be able to plan this agent under stochasticity such that, of course, the agent moves to the goal, but in a generic sense, such that the agent maximizes all the summation of rewards that it gets on the way. And in order to do that, in order for my agent to maximize the summation of all the rewards that it gets on the way, let us also define the third and the last most difficult thing, which is called as the utility. So utility is the total summation of all rewards that the agent, I do not know how much will it get, so I say is expected to get from the state S, and that's denoted as US. So what's the total summation of all rewards that I'm expected to get from a state S? How do I go after state S? So I just add when operating under an optimal policy. So all I say is that from the state S, how do I make a motion? I don't know. There's a policy that has been given to me and I keep moving by that. I sometimes slip, I sometimes don't slip. However, when I reach the goal and I get this award of reaching the goal, I do all the calculations. I spend so much money here, I got so much money from there, I spent so much money here, I got so much money from there. Summing all of it up, how much is the total money that I have? That is what is called as my utility. And this time I'll get a little bit informal and I'll try to calculate my utility for this problem. So let's say I was at 1, initially, and after going from 1, I applied the action right and I did not slip, so I went through 1, 2, and our SAS dash is minus 0.1. So now I'll not write RSAS dash and write it explicitly, I'll just mention it under the arrow. So previously under the arrow I was writing everything that lets you decide what the reward should be. Now I'm just writing down the reward directly. From 1, 2 I again take a right and I do not slip. So I reach 1, 3 and I get a minus 0.1 as the reward. From 1, 3 I again take a right. This time I slip, and because I slip I collide and I stay at 1, 3. And because I stay at 1, 3, I incur in a minus 100 as I broke something, so I'm happy to this extent. But life goes on. No matter I get hurt, I'll not stop moving. Again I try a right, then I this time reach change of axis. Oops. So let me quickly change the axis. My bad. So 1, 1, 2, 1, 3, 1, 4, 1, 1, 1, 2, 1, 3, 1, 4, 1. Okay, so I again 3, 1 and 4, 1. So again to the right, this time I did not slip, so wonderful, it becomes minus 0.1. Now I take a up and I do not slip, so minus 0.1. and I reach a 4-2. I again take a up, I collide, I slip, I collide. Maybe I collided with this wall and I reached back at 4-2, so it's minus 100. Then life again goes on, I take a up, I reach the goal, and of course I get a plus 1000. So then I do the total, I say total rewards is equal to minus 0.1 plus minus 0.1 plus minus 100 plus minus 0.1 plus minus 0.1 plus minus 100 plus the terminal reward of 2000. So that is 1000 minus 200 minus 1234. 0.4 is equal to 799.6. Now I don't say this is the utility because of one reason, that if I follow exactly the same sequence again, I'll take the same action as told by me, by someone very knowledgeable. So my actions will remain the same because of somebody very knowledgeable telling me which is the best action to take. But where do I reach? This is decided by God, or this is stochastic. And hence I may not reach the same spot again, and hence my sequence will differ. Once my sequence will differ, my total rewards will differ. Hence my total rewards will differ, so I will get in a different value. So I don't say this is the utility, I say this is the indicative utility informally, assuming the action selecting were optimal. So assuming best selected actions. So what really is my utility? Again, speaking informally, utility of S is average of such infinite runs. So we did it once, do it infinite times, takes the average, and that's why I said expected. And whatever you get, that is what is your utility. And that brings me down to a very fundamental difference written once more. So we have three terms: policy, reward, and utility. Policy denoted by pi of s, reward by r SAS dash, and utility by pi s. Policy just says which is the best action, up, down, right, left. Which is the best action to be taken from a state S? We haven't calculated it up, but then that's the entire lecture about. So policy just says at state S which is the best action. Utility states from that state, if you go on reaching the terminal state or the goal, by the way, you have to stop at the goal. The game ends. Any game ends when you reach the goal. Tic-tac-toe, you get 3 consecutive game ends. This institution, you get your final degree, your BTech game ends. You can no longer do anything in this institute. So, utility is a total summation reward, is a total summation of all rewards that you get all the way up to the goal, and a reward is something that you get immediate. So we say reward is short term, immediate, utility is long term gains. So that's also to say what's your short term gain and what's your long term gain. And normally policy is very different from the other two, so it's rarely confused, and these are more confused. So let's take in examples. Right now what you're going through is a lot of pain, so the reward of watching this lecture is negative. It pains, it gives headache. You would have better open the new tab and watch the latest movie. You would have better play the video game. That gives a sense of pleasure Watching this monotonous lecture, it completely pains your head. So, the reward of watching this lecture is negative. You're missing out a lot of fun that people are having outside, but still you are taking that action. Why? And the answer is simple, because even though the reward, immediate pain, is negative, but later on, when on the interview table somebody asks you a question on AI, and because you watch this lecture, you can answer it, and you get that amazing N lakhs per annum package, and you're happy. So, was it possible because of only your last action of having sat at that interview and answered the question? No, it was possible because you took this pain right now. So, as we say, the reward of this lecture is highly negative, but that helps you win that jackpot prize later on. So the utility is positive. So as to say, for this example as well, why does the agent take the pain and go around over here? Why not just do nothing? Because even though it may pain in going here, it will eventually reach a goal and it will get the jackpot. So to get the jackpot, you have to take pains in life. Once you don't take that pains, you don't get that jackpot. So the reward is negative, but the utility is positive. The utility is long sighted. It says, what will I get now, next, 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 all the way up to the end. So utility summits everything till the end, and therefore things will have positive utility. So you learn something new in life, even to walk, you fall down, reward negative, but then you can walk and do all the amazing things. The utility of doing that may be positive. And therefore, funny thing about life, no pains, no gains, no negative rewards, no high terminal rewards, which means that even if some things have negative reward, most of the things, even if they have negative rewards, it doesn't mean they are bad. The utility will be positive, or from that state, you'll reach a state which will have that jackpot offer. So, in short, going from here to here has negative reward, positive utility. Listening to this lecture has negative reward, positive utility. Learning how to walk has negative reward, positive utility, and so on and so forth. Most of the things in life. Now let's take in the problem of calculating these three values now, which is the only thing I need to tell you. Definitions okay. How will you end up in calculating all these up? Finally, I just need a policy function so that my agent knows how to move in this particular world. And therefore, let us do it up. So, take a small example. I am at the state 2, and now can I mathematically represent the utility of the state 2? That's the question. So can I mathematically represent this in the form of an equation? That is what I'll do. And the way that I'll do it using generic notation first, which will be confusing. And after that, I will come to this example and see how simple it is. So let's do it under the generic terms first in order to define the utility of a state S. So in order to define the utility of a state S, I say I am at a state S and I apply an action A. After applying an action A, God plays its move, and I do not know which move will God play. I could reach S1, S2, S10, S15, S21. But in general, I reach a state S dash, and the probability of reaching the state S dash is what is given as TSAS dash, and the reward is given as RSAS dash. So this is what I control, or the agent controls, and this is what God controls. So many actions would have been possible, but I control which action is to take, and this one is controlled by a God. So let us define the utility of a state S. Now, it's like divide and conquer. It's like recursive call. In order to define the utility of a state S, I will assume the utility of S dash is known. So I assume utility of S dash is known. In order to make a solution expression, what that means is from S dash, after all the slippings, after everything up, all that I know is the cost in going, or the total summative rewards in going from S dash all the way up to the goal is what is given as US dash. So let's do it. So I say when I go from S to S dash, I incur in, so what I collect as reward is RSA S dash, and from S dash to goal, all I collect is U of S dash. So a small way by which this can be denoted in what we classically did is like this. From S to S dash, I collect SAS dash, and remember S to S dash is one of the many branches possible like this. And from S dash to the goal, I will get a US dash. What is my US? It is here. What's the total summative rewards? So it's same as the Dijkstra's, except for Dijkstra's it was cost. So we had to minimize. Now it's rewards which we need to maximize. So of course I say this is equal to this plus this, or U of S is equal to, how much did I give? RSA S dash. From S dash to goal is U of S dash. And many such S dashes possible. God controls these moves. So this is multiplied by the probability of getting to S dash given SA, and what happens is, how do I get A? I control the action. The actions are controlled by me, so it's maximized over all the actions. And this is what I define as a utility of S. If instead RSAS dash you have RSAS dash rewards only defined on state S, then it becomes easy. So it becomes RS, which can come out of the probabilities and everything, plus max over A, P S dash by SA, utility of S dash. So this was in short expression which was very intuitively done. Want to know how it's practically happening? Don't understand these weird expressions, so let's do it practically for one of them. Let's do it for 2, 2. So from 2, 2, I can take in any one of the actions. I can take in a up, I can take in a down, I can take in a right, I can take in a left. So I'll take in a down and I'll only solve it for down. You do it for all the rest. So I say utility of 2, 2 is equal to max over this expression plus this plus this plus this. I'll get 4 expressions. So it's maximum over utility of taking an action up 2, 2, utility of taking an action down 2, 2, utility of taking the action left to 2 and utility of taking the action right to 2. Now God controls which state do I reach, and I can reach any one of the three states. So from 2 to, if I apply down, I can either reach 1 2 with a probability of 0.1. I can reach 3 2 with a probability of 0.1, or I can reach the correct one to 1 with a probability of 0.8. From 1 2 to goal, the total utility is U12. From 2 1 to goal, the total utility is U21. From 3 2 to the goal, the total utility is U32. So in minimax kind of thing, you can assume that this utility is given, that assumption. So this is given. And what's my total reward over here? So let's say R1, R2 and R3, where we know it's it's simple, so each one of them is minus 0.1. So what's the total? If I take this branch, what's my total gains? So it will be 0.1 times whatever are my gains here plus 0.8 times whatever are my gains here plus 0.1 times whatever are my gains here. What are my gains here? So I get R1 immediately, and from 1 2 to goal I get U12. I get 0.8 immediately, and from 2 1 to goal I get U21, and I get R3 immediately, and from 3 2 to goal I get 3 2. So solve this up. R1, R2, R3 is known as minus 0.1. You get this value, do it for all of them, and you know exactly how much will be U22. However, I cannot get utility values like this because this is unknown. And similarly over here. So these are unknown. So, but I just wanted to make in an expression, and one thing I have is that the expression is correct. And because the expression is correct, at least I've derived in an expression. How to solve it, we'll care about it later. Now let's define my policy. So policy is, there were 4 branches over here. Which branch do I select? I select this one, this one, this one, this one, and that's my policy. Policy is the only thing that I need to calculate. So policy is nothing but argmax over A, and then you get exactly the same expression, P S dash given S A. So I mean, which A did you choose in order to get this maximum? That is your policy. So it will be up, down, right, or left. And that's the one that I will need to calculate it up. Now, assuming that you know what is utility, what is policy, what is a reward, let me do one thing. Let's take in a small map and let's try to intuitively understand what these terms are. So here's my small map. And some of them are obstacles. So it's exactly the same map and some of them are obstacles. So this is what I say is utility of S, and this is what I say is the policy of S, and this is what is the goal. So intuitively looking at it, what I expected from here, I will go here. From goal, you cannot take any action. I'll go here, I'll go here. So I'm always going towards the goal. That's what your A-star algorithm would have done. This is what I normally expect. And normally I expect that goal, of course, has the plus 1000 terminal utility. Here, I'll just take this step up. So it should be 999.9. So minus 0.1 reward. Here also, I should directly go here. It should be 999.9 reward. Here it's intuitively difficult because 10% of the time I'll collide because of this, 10% I'll collide because of this. So 20% I always have to collide. So it will be much lesser some value. And these are the values that I need to calculate. So I only take the correct one as 80% of the time. And then 20% of the time I'll have a big reward. That will be here intuitively. And that's how I'll fill in all these values. Now, let's look at a couple of interesting things. The first interesting thing is that I was taking minus 0.1 as the cost of colliding. What if instead of a minus 0.1, I take it as minus 1000? So if you take it as minus 1000, taking in one step has so less of a negative reward that collision minus 100 is nothing in front of it. So effectively it comes that you are trying to just minimize the number of steps. You stop caring about collision because the cost of moving is much harsher than collision. On the other hand, if you make this minus 0.1 as, let us say, nearly 0, so it's approximately becomes equal to 0, now it doesn't matter. It absolutely doesn't matter how many steps do you really want to take, and therefore what you do is, instead of doing anything, you just avoid a collision at any point of time. So the first interesting thing is that these are the interesting things about how these numbers play an important role. And one of my last things for today will also be that these numbers, deciding them becomes very difficult in these algorithms.